Hi everyone, welcome once more to this YouTube channel, Best Science Brain YouTube channel. You're still with your online moderator, Dr. B. Today, we're going to continue the lecture on chemical bonding, which we did last time. We couldn't finish it. We did chemical bonding 1, and this is chemical bonding 2. And hopefully, we're going to finish this lecture today on chemical bonding. Looking at all aspects of chemical bonding, valence bond theory, hybridization, shapes of molecules, bond polarity, dissociation energy, bond Haber circle. So you're welcome once more to the channel. If you are seeing the channel for the very first time, or this is your first time timer, please, or you're not a subscriber to the channel, and the video is playing on your phone or your gadget, on your tablet, look for the subscription button, an icon that looks like a tiny bell below the video or above the video. Search for the subscription button and then tap on the subscription button only once and get subscribed to the channel. The subscription to the channel will help you, so whenever we post any video, you get the notification right on your phone and right on time. You can still share a video to students, not only at your own level, students in other high institutions, your friends, your relatives, your sons, your daughters. They all need this video to grow in sciences. So if you're in high institution, first year precisely, or you're doing an A-level course in chemistry, this topic is for you. This particular session, chemical bonding 2, is particularly for you. So welcome all subscribers. We welcome all viewers over the world as you stay connected to the channel. To start with this video, we'll first of all summarize the last thing we did in chemical bonding 1. In the last aspect of our video in chemical bonding 1, we are looking at the geometry of molecules, or the shape of molecules. And this is a table summarizing what we did. And I said, when a molecule had this formula AB2, of this nature AB2, where A represents the central atom, and B2 are the atoms bonded to the central atom. Now, such molecule, if number of lone pairs on A, that means A has no lone pair on it. So if A has no lone pair, number of lone pairs is 0 on A. A is the central atom. Number of atoms bonded to A is 2, as you can see, B2. B is the atom bonded to A. Then such molecule is, say, example is BeH2, where B, beryllium, is our A. And then H2 is our B2 in this case. And beryllium has no lone pair on it. Such a molecule is said to have linear shape in chemistry. Okay, the next one we look at was a molecule with the general form AB3, where A is the central atom with no or 0 lone pair on it, and is bonded to 3 atoms, so B3, 3 atoms of B, bonded to be like beryllium trichloride, BeCl3. Such a molecule, boron trichloride, BeCl3. So such a molecule will have what called trigonal planar shape. Then again, when a molecule is of this form AB4, where A is the central atom, like carbon in this case, bonded to 4 atoms, which is hydrogen. And then the central atom has 0 lone pairs. Nothing on the central, no electron on the central atom. Such a molecule is said to have tetrahedral shape. The other shape we look at is when a molecule have this shape, have this formula AB5, whereby the molecule has A at the central atom with 0 lone pair, then 5 atoms bonded to A, example BCl5, phosphorus pentachloride. Such a molecule have what called trigonal bipyramidal shape. So the examples we have studied so far from chemistry bonding 1 are molecules whose central atoms, which represent as A, has no lone pair, but bonded to 2, 3, 4, or 5 atoms to it. 2 atoms bonded to the central atom is linear shape. triatoms bonded to the central atom is trigonal planar, like in boron trichloride. 4 atoms bonded to the central atom gives you tetrahedral shape, like in methane. 5 atoms bonded to the central atom A is trigonal bipyramidal. Mind you, the central atom will have no lone pair for this to work. So any molecule that conforms to any of this configuration will have the required shape as we listed them on the whiteboard. So having done that, we're going to look at another example. A molecule with this formula AB6, whereby we have a AB6, this kind of molecule, where A has 0 lone pair on it. Number of atoms bonded to A is 6. Example, maybe sulfur hexafluoride. Such a molecule has what kind of shape? This molecule has what's called octahedral shape. Octahedral shape. So you can see that. Like, let's look at the bonding. Sulfur SF6, that's the formula. We have 1 atom of sulfur and 6 atoms of fluorine. The atomic number of sulfur is 16. That is 286. Sulfur is the central atom. Why is sulfur the central atom? Because it has only 1 atom. Sulfur has only 1 atom in the molecule. So let's now draw the Lewis structure of sulfur. So let's represent only the 6 electrons in the atmosphere. Have 1, 2, 3, 4. We have 6, 5, and 6. Then we need 6 fluorine atoms. 6 fluorine atoms, and you know that fluorine is the halogen. The number is fluorine is 9. That is 2, 7. So fluorine is the halogen, but we require 6 of fluorine atoms to bond to 6 to bind to 1 sulfur atom. So you now have fluorine, 1 atom here, 2. Let me use asterisk. 1, 2, 3, 4, 5, 6, 7. Having 7 atmospheres. So we need 6 of this. That means each of the fluorine atoms will move around the sulfur and bind with 1 sulfur electron. So let's see how it goes. Now we have 1 electron from sulfur, 1 from fluorine, bonded here. 1 from sulfur, 1 from fluorine, also here. So you see that sulfur is 286. You see, start wondering, since we need 6 fluorine atoms, what then? How will the remaining 4 bond to this sulfur? What's going to happen is that these 2 paired electrons will unpair themselves to accommodate the remaining 4 fluorine atoms. So these 2 paired electrons will now unpair, separate, so that they accommodate the other 4 fluorine atoms. See, this is what is happening. So another fluorine atom comes in there, another one comes in there, another one goes there, another one goes in there. So you see the bonding is now complete. A bond formed here, a single bond, another single bond, single bond, single bond. So sulfur at the center bonded to 1, 2, 3, 4, 5, 6. 6 fluorine atoms. You look at this sulfur at the center, there is no lone pair around it. All the electrons around this sulfur are the bonding pairs of electrons, no lone pair. So as we said, it conforms to the formula AB6, where the central atom being sulfur has no lone pair, and they have 6 electrons, 6 atoms bonding around it. So this structure gives us what's called the octahedral shape, which we described in a former or previous video. So having done that, the next thing is this. We are seeing the situation whereby the central atom has no lone pair. When it has no lone pair, it's bonded to 2 atoms, linear shape. No lone pair on the central atom bonded to 3 atoms, gives us trigonal planar shape. No lone pair on the central atom bonded to 4 atoms gives us tetrahedral shape. No lone pair on the central atom bonded to 5 more atoms gives us what we call trigonal bipyramidal shape. No lone pair on the central atom bonded to 6 atoms, as we have on the board, gives us octahedral shape. Now, we won't do a situation whereby what if the central atom has a lone pair? For instance, let's look at ammonia. Ammonia has a central atom, nitrogen bonded to 3 atoms. Central atoms bonded to 3 hydrogen atoms. So, can we say that ammonia is trigonal planar? Just like the example we saw a few minutes ago. We would say that boron, it looks like this, boron, BeCl3, boron trichloride is trigonal planar. So do we say that ammonia is also trigonal planar because they look like, it's not as if they have the same structure, AB3 each? No. Ammonia don't have trigonal planar shape, unlike this one that has trigonal planar shape, because in ammonia, the central atom has a lone pair. So look at the bonding ammonia. Ammonia have N plus 3H. So nitrogen, atomic number is 7, write the electron configuration 2, 5. Hydrogen, we have 1. Atomic number is 1 electron decay shell. Now let's do the bonding. The Lewis structure of nitrogen give you N. 1, 2, 3, 4, 5. 5 valence electrons. Then you need one hydrogen atom on the 3 sides. So you see that nitrogen requires 3 to become complete. 1, 2, 3, or 8 minus 5, 3. It requires 3 to reach octet state. But how are you going to share with hydrogen? This 3 requires, you're going to share it among 3 atoms. So divide the 3 by 3. That means it's going to give 1, 1 to each of the hydrogen. We now have this bonding taking place in this form. So 1 from nitrogen and 1 from hydrogen. Okay, another 1 from nitrogen this side, and then 1 brought by hydrogen, 1 from nitrogen, and 1 electron from hydrogen. So nitrogen has maintained the octet state of 2, 4, 6, 8, while each hydrogen atom maintains the duplex state. So you see that the central atom, which is nitrogen, has a lone pair on it. So this structure cannot be trigonal planar shape. Now, according to the valence share electron repulsion theory, as we said in the first video, the lone pair repels so much or has a great repulsion effect on the bond pairs. The lone pair, because the lone pair is delocalized around, is not bonded to any atom. So it moves around to repel any adjacent bond pair. So the repulsion between the lone pair and bond pair is greater than repulsion between the bond pair and bond pair electrons. So that means the shape of ammonia cannot be a straight shape like this. No, because of the repulsion, this is the wrong shape for ammonia. So what do? So because of the repulsive effect, so ammonia will have a kind of twisted shape. But we don't call it twisted shape. The bond will bend. The repulsion of the lone pair shift the electron by the adjacent sides to make an angle. So you can see that ammonia has a twisted shape. But in chemistry, we don't call it twisted shape. This shape of ammonia is called trigonal pyramidal shape. Trigonal pyramidal shape. Let's draw it up. Trigonal pyramidal shape. Remember, it is not trigonal bipyramidal. Trigonal bipyramidal is a shape of a molecule like BeCl5 that has no lone pair on the central atom bonded to 5 atoms. BeCl5 is trigonal bipyramidal, but this is trigonal pyramidal shape. So ammonia has trigonal pyramidal shape. So why is this so? So if you look at the structure very well, we can make a little construction from this point to this other point. We project them and then cut it off. have a kind of pyramid, a kind of triangle, sorry, inverted triangle here with the dotted lines. We move up, we now form a kind of a pyramid sitting on a triangle. So that is why we say that ammonia has trigonal pyramidal shape. The bond angle in ammonia is about 107.5 degrees, or about 107 degrees. That's the bond angle of ammonia trigonal pyramidal shape. So you see, because of the lone pair on nitrogen, ammonia does not have a trigonal planar shape. Look at the difference. Look, this is ammonia. Then let's review BCl5, BCl3, sorry, boron trichloride. This is ammonia. The structure look alike. But if I say to have trigonal pyramidal, I say to have trigonal planar. So what's the difference between the two? In this one, the boron atom is 5, that is 2, 3. The number is 5. The central atom is boron. It has 3 electrons in the outermost shell. That is 2, 3. We need chlorine. Chlorine is the halogen, and each chlorine bring 1 electron, 1 electron, and 1 electron. So the bonding in ammonia and boron trichloride look alike, but there's a difference. In ammonia, the nitrogen has a lone pair. In boron trichloride, the boron has no lone pair. It only has 3 bond pairs. See the difference? So we're going to call this shape trigonal planar shape. Call this one trigonal. This one, the shape of this one would look like boron, chlorine, chlorine, chlorine. Sorry, chlorine coming down here, the repulsion, chlorine coming down here. So this is trigonal planar shape, but it's called trigonal pyramidal shape. See the difference between the two molecules. Then another example is water molecule. Water is also another molecule whose central atom has lone pairs. In water we have oxygen bonded to 2 hydrogen atoms. Oxygen here is the central atom. Why is this so? Because it's the element that has only 1 atom in the molecule. So let's draw this, write the electron 8, 2, 6, then this is 1. If I draw a Lewis structure of oxygen, I have 1, let me do it by the side, 1, 2, 3, 4, 5, and 6. The required hydrogen has only 1 electron in the atmosphere, and the hydrogen there. So oxygen requires 2 electrons to become complete, while hydrogen requires 1, 1 each. So the central atom requires 2. The central atom is the determinant or determining factor for you to know how many electrons to be shared. So the central atom requires 2. So you're going to share between 2 atoms. So divide these 2 requires, or from here 8 minus 6 is 2. Divide these 2 by 2 since it's going to share between 2 atoms. That is 1, 1 each. So each oxygen atom will bring 1 electron for each hydrogen atom for them to bond together and form covalent bond. Now you see that oxygen has a greater lone pair than nitrogen in ammonia. Oxygen has 2 lone pairs of electrons, while in ammonia we saw that nitrogen has only 1 lone pair. So that means there's going to be a greater repulsion in oxygen compared to ammonia. So if 1 lone pair on nitrogen could bend the molecule to have a trigonal pyramidal shape, 2 lone pairs in oxygen will now have a greater repulsion effect. So that oxygen will now have a kind of twisted or distorted shape. I mean, water will have a kind of twisted or distorted shape, so bending more than ammonia. So we now see that water in chemistry has what we call an angular shape, angular or V shape. So let's draw the structure up. Water has angular or V shape. Some people call it bent shape. So water has angular V or bent shape. So this is the shape of water molecule. So why is it called angular shape? Look at it. If you extend this line inwards to the center of oxygen, they will join. And then if you use a dotted line to cross this end, you form a kind of triangle. So when water has an angular shape, then or it looks like an inverted V shape or bent shape. The bond angle in water is small, approximately about 105 degree. So the more the bending or twisting of the bond, the smaller the bond angle. So we are seeing examples of molecules whose central atoms have lone pairs of electrons, have lone pairs. So we're going to take a little exercise now before we continue. So look at this question that says, state the shapes of the following molecules: aluminium chloride, beryllium difluoride, phosphorus pentabromide, and then phosphine. Find the shape of the following molecules. Let's start with the first one. For this first one, aluminium chloride, you split it, aluminium and 3 chlorine atoms. The aluminium has atom number of 13. You write the electronic configuration, which is 283. Chlorine has 17, atom number 17. Write the EC 287. The Lewis structure of aluminium will have 3 electrons in the outermost shell. Chlorine, each of them will have 7 electrons in its outermost shell. 7. So aluminium is the central atom because it's the one that has only one atom in the compound. It needs 3 to pair up. Divide this 3 into 3 chlorine atom into 3. It's going to be 1. So you're going to bring 1. Each chlorine bring 1 to bond with 1 aluminium. So we now have aluminium, 1 electron for aluminium, 1 from chlorine there. 1 for aluminium, 1 from chlorine. 1 for aluminium, 1 from chlorine. Then you can put the lone pairs on chlorine, the 6 lone pairs on chlorine. Okay, so you use asterisk. 2, 4, 6. 2, 4, 6. 2, 4, 6. Look at this structure very well. You see that aluminium, what structure do you predict aluminium chloride to have? You see that the central atom of aluminium has 3 bond pairs, but no lone pair around aluminium. And remember that I told you that when a molecule has, look at this formula I gave you, AB3, a central atom with no lone pair bonded to 3 other atoms, that molecule have what called trigonal planar shape. Trigonal planar shape. So aluminium chloride has trigonal planar shape. If you look at the structure, it will look like that of boron chloride that we drew some minutes ago. Trigonal planar shape. So aluminium chloride has trigonal planar because the central atom has no lone pair and then bonded to 3 other atoms. So that settles aluminium chloride. Go to B, beryllium chloride. What shape does this molecule have? Let's look at it. Beryllium chloride contains beryllium at the central atom and 2 fluorine atoms. Beryllium has the number of 4. The EC is 2, 2. Fluorine is the halogen. We have 7 by, that is 279, 7 electrons. Then beryllium will have 2 electrons in the outermost shell, 1, 2. While fluorine has 7, according to the Lewis structure, 1, 2, 3, 4, 5, 6, 7. We need 2 fluorine atoms. 1, 2, 3, 4, 5, 6, 7. The central atom needs 2 extra. You're going to share these 2 between 2 atoms. So divide the 2 by 2. That is going to be 1, 1. So they bring 1, 1 for sharing. Now I have beryllium is 1 electron. Fluorine brings its own electron to bond here. Have this come here. So beryllium and fluorine bring 1 electron to bond to this point. So you can see that. So if you look at beryllium, beryllium has 2 bonding pairs of electrons close to it, but no lone pair on it. So this is the molecule that has, central atom has no lone pair, but 2 bonding pairs. And as I told you, a molecule that has this formula AB2, whereby the central atom is bonded to 2 atoms, and the central atom has no lone pair, is said to have linear shape. So beryllium has, beryllium difluoride has linear shape, a bond angle of 180 degrees. So you see that. So that is the very simple questions to answer. So when you're given the question, try to know the bonding sequence and then predict the kind of shape some people can have. Look at number options, the number C. C is phosphorus pentabromide. In this one, have a phosphorus. The number is 15285. Then plus 5 bromine atoms. Bromine is a halogen. So the valence electron, may not start talking about electronic configuration here, but valence electron of bromine is 7. 7 valence electrons in bromine. That's easy for you to do. So phosphorus has 5. 1, 2, 3, 4, 5. Bromine will require 1. It's a halogen. It needs extra 1. So we're going to bring 1 bromine here. Then the lone pairs 2, 4, 6. Then the 7th one making it 8 from phosphorus. Then another bromine here. 2, 4, 6. 2, 4, 6. Then 7. Then 1 from phosphorus 8. Another bromine, bring 1 electron here to complete this place. Then you have 2. The remaining lone pairs. They now have, we have used 3 bromine, remaining 2 bromine. There are 5 of them. So what's going to happen? These 2 pair will now unpair. That's why we say phosphorus is one of the elements that undergoes or that obeys or disobeys the octet rule. So phosphorus undergo what we call the expanded octet theory. So the 2 will unpair to accommodate the remaining 2 bromine. So you now have bromine again, bring electron here. Have this, the lone pairs. Another bromine, bring its electron here. The lone pairs will now be there. So you look at the central atom, phosphorus, it has no lone pair. Look at it very well. We only have bonding pairs. 1, 2, that is share of bromine, 2, 1, 2, 3, 4, 5. 5 bonding pairs, but no lone pair. So this molecule conforms to the formula of AB5, whereby the central atom has no lone pair, but bonded to 5 other atoms. And such a molecule is said to have what we call trigonal bipyramidal shape. Trigonal bipyramidal shape. We'll now quickly look at number D, phosphine. Phosphine, PH3. In phosphine, 1 phosphorus atom bonded to 3 hydrogen atoms. Okay, phosphorus, as we have done before, has 5 valence electrons around it. That is phosphorus. The hydrogen will bring 1 electron here, bond here, bond here, and bond here. You see this? So this molecule confirms the formula AB3. Central atom and then 3 atoms bonded to it. So we'll be tempted to say that this molecule has trigonal planar shape. But does it? No. It doesn't have trigonal planar shape because there's a lone pair here. And this lone pair will not make it be trigonal planar. Rather, it's going to be trigonal pyramidal shape. So phosphine has trigonal pyramidal. Trigonal, this C, trigonal bipyramidal. D, trigonal pyramidal. So this bond, why is this so? Because this lone pair repels this, repels that. Then the shape of phosphorus will look like the shape of ammonia we studied today. In ammonia has similar structure. Ammonia also has trigonal pyramidal shape. So having done that, we can go over to another thing. Next, we are looking at some bond properties. Covalent bond has some properties. We'll discuss one of them in the first video. The one we discuss was bond order. Other properties of covalent bond include bond length, bond polarity, and bond dissociation energy. So in this video, we're going to talk about bond polarity and bond dissociation energy. So let's start with bond polarity. Polarity is an uneven distribution of electron density, which occurs when atoms of different electronegativities are bonded to each other. I repeat, polarity is an uneven or non-uniform distribution of electron density, which occurs when atoms or different electronegativities are bonded to each other. Then what is the polar molecule? A polar molecule is a molecule that has a dipole moment formed by or formed from two atoms of large electronegative difference. Formed from two atoms of large electronegative difference. So let's try to explain a little on this bond polarity. Now, let's consider a molecule like HCl. How is HCl formed? HCl is formed between two nonmetals. Hydrogen has one valence electron. Chlorine has 7 valence electrons, being a halogen. So since both are nonmetals, they will share electrons. Hydrogen will bring 1, while chlorine will bring 1 to complete its outermost shell. So this is pure covalent bonding. But when we look at the two atoms are dissimilar atoms, that is two different atoms. Hydrogen tends to be electropositive, while chlorine, being a halogen, is highly electronegative. They now have a bond pair to share here. The question is, will they now share this bond pair equally? The answer is no, because chlorine is more electronegative than hydrogen. That means there's going to be a tug of war existing between these two. They're going to drag the electron, drag for who has the upper hand. So in actual, have you been that we have two hydrogen atoms together sharing this electron? We have two chlorine atoms sharing the electron. I mean, this is chlorine, or hydrogen. There'll be no tug of war. The distance between the nuclei and the electron, the point of sharing electron, maybe for each of them would have been maybe 0.15 cm, 0.5 cm from here to there. The same equal distances, 0.5, 0.5, and also 0.5, because this is pure covalent, because the two elements are the same, they're homonuclear, they have the same electronegative difference. But in this case, we don't experience such. Now, because chlorine is more electronegative than hydrogen, what then will happen? Chlorine will pull the electron more than hydrogen. So that means the electron move closer to chlorine than hydrogen. If the distance between hydrogen and electron is 1 cm, the distance between chlorine and the electron now will be around maybe 0.5 cm. They just estimate like that, 0.5 cm. To show that the electron move closer to chlorine than hydrogen. Then what's the net effect? That will cause the bond become polar. So look at the bond. That would have been covalent bond. So in chemistry, what we now do is we now represent the bond with a dotted line, showing that the electron is being dragged, the bond is polarized. And since hydrogen appears to be losing the electron, we'll give it a partial positive. Remember, it did not lose completely, because it cannot lose and become empty. But it will lose partially, while chlorine will appear to be gaining, give a partial negative sign. So this attraction between the unlike charges is what's called the dipole attraction. And that means this molecule become polar or soluble in water. So you see that. So how to predict polarity is easy. Sometimes you may predict by looking at the position of the element in the periodic table. For instance, hydrogen is bonded to an element in group 5, like nitrogen, or so in group 6, like oxygen or sulfur. In group 7, like halogens. So hydrogen is bonded to most of these elements in group 5, 6, 7. It is sure that the bond is 90% going to, or 95% supposed to be polar. Like ammonia is a polar molecule. Ammonia, nitrogen is in group 5. Oxygen, water is polar. Sulfur, hydrogen sulfide is polar. Halogens, chlorine, bromine, iodine to hydrogen, the molecules are all polar. So that is not the only way to estimate polarity of a molecule anyway, but we can just try to have a guess. When there is a wide gap between the two elements in the periodic table, that molecule is likely to be polar. But if there's a narrow gap, then the molecule has a slim chance of being polar. So having done that, we now look at what if we have a molecule of the same electron, the whole molecular molecule, a molecule made of similar atoms like hydrogen, chlorine, hydrogen, iodine, bromine. Are these molecules polar? The answer is no. The answer is no, because the molecules will have zero electronegative difference, because the difference between the electronegative value of chlorine and that chlorine atom will be zero, because we have equal electronegativity. The difference between the electronegative value of hydrogen and that hydrogen atom will also be zero. So homonuclear molecules are usually non-polar because they have zero electronegative difference. Then, how do we predict what range of electronegative difference can make a bond polar? For a bond to become polar, the electronegative difference between the two atoms, negative difference between the two atoms, will be of the range 0.4 to 1.7. So when the difference between the electronegativity of two bonded atoms lies between this range 0.4 to 1.7, which is mainly for the ionic compounds. Because ionic compounds always solve in water. So when a covalent molecule has the kind of a difference in the electronegativity between the bonded atoms, that covalent molecule is said to be polar or polar. So there are some factors that determine polarity of molecules. So it's not only the difference in electronegativity. The other factors determine the polarity of molecules. So look at this. Let's look at these factors in a jiffy. Okay, let's look at the factors that determine the polarity of molecules. As mentioned before, the first factor that determines the polarity of a molecule is electronegative difference. Polar bonds occurs if two atoms in a molecule have, polar bonds occur if two atoms in a molecule have wide difference in electronegativity, leading to the creation of a dipole. As I explained before, when two bonded atoms in a molecule have large difference in their electronegativity, then that bond is likely to be polar. As I use HCl, ammonia, and water molecule as illustration. And I told you that the difference in the electronegativity should range from 0.4 to about 1.7. Elements in the periodic table have what we call electronegative values that have been calculated by Pauli. So we're going to see that in our next question. The next factor that determines the polarity of molecule is the molecularity or molecular shape or geometry of the molecule. So sometimes a molecule can consist of two atoms that have large difference in the electronegativity. But at the end of the day, you find that that molecule is non-polar. So what does it mean? What factor accounts for that? So apart from the electronegativity difference, we'll still consider the shape of the molecule. So I read, if a bond is polar, the overall polarity of the molecule depends on its shape. A polar molecule must be asymmetrical. A polar molecule must be asymmetrical. Asymmetrical can also be called unsymmetrical. Okay. So for a molecule to be polar, it must be asymmetrical so that the dipole moment do not cancel each other. So in a polar molecule, the dipole moment cannot cancel each other. So even if a molecule has large difference in electronegativity of bonded atoms, the polar dipole moments should not cancel themselves. Because they should cancel themselves, that means the molecule is symmetrical and cannot be polar again. Another factor that affects the polarity of molecule is presence of lone pairs. Yes. As we are studying the shape of molecules, Lone pairs helps determine the shape of molecule by creating a negative area around the central atom. Lone pairs, molecules that have lone pairs tend to be bent or twisted, and that increases their polarity. So let's take a question to explain more of this. So let's look at the question on the board that says predict the polarity of the following molecules. Number 1, HCl, 2, ammonia, 3, chlorine molecule, 4, SO2, 5, CO2, 6, CH4 methane. And then we're giving the E values of the element. The E value, E here means the electronegative values of the elements. So let's look at the first one. The first one, hydrogen and chlorine are bonded together here. The E value of hydrogen is 2.2 for the table. Chlorine is 3.16. We look for the difference in the electronegativity. The bigger value minus the smaller one. 3.16 minus 2.2. So when we do that, we obtain 0.96. This value is large because we see that for an element to be polar, the range is from 0.4 to 1.7. So this is more than 0.4. Now, it's expected to be polar. But also, before we consider it's polar, let's look at the geometry. If we look at the structure of this, these two they consist of two elements of large difference in the electronegativity. So they're going to be, the bond will polarize. With this one, pull the electron more to itself, being partially negative, and this one being partially positive. So this bond is the polar bond. The bond depolarized. So HCl should be a polar molecule. Now going to number 2. Number 2, we're given ammonia. Ammonia is NH3. Nitrogen bonded to 3 hydrogen atoms. Let's just consider one nitrogen and one hydrogen atom. So the electronic difference of nitrogen is, the native value of nitrogen is 3.04 and of hydrogen is 2.2. We find the difference between them, 3.04 minus 2.2. You see, the difference between them will give us 0.94. Also, a large value that is above 0.4. That will help us to suspect this molecule as being polar. But before we conclude that it's polar, let's look at the structure of ammonia. We've done the geometry of molecules. Ammonia has what we call trigonal pyramidal shape. Because a lone pair on nitrogen and then twisting the shape. And as we say, the presence of lone pair helps to increase polarity of the molecule. So this molecule will polarize. The bond will partially, the electron will drag between nitrogen and the hydrogen atoms, with nitrogen having the upper hand to pull the electrons. 3 here because it's dragging it with 3 hydrogen atoms. While each hydrogen atom become partially positive. So ammonia is the polar molecule. The shape is not symmetrical. So it's a polar molecule. And also we have a large electronegative difference between nitrogen and the hydrogen. Going to number 3, chlorine. Number 3, chlorine. We have 2 atoms of equal electronegative value is chlorine. So the difference between the two of them will be 0. 0. So chlorine for sure is a non-polar molecule. Going to number 4, which is SO2. In SO2 we have sulfur, which is 2.58 electronegative value. Oxygen atom, picking one of them, 3.44. The difference in the value will be 3.44 minus 2.58. We'll subtract and look at the value and see, look at the shape of the molecule. So the difference will give us 0.86, something large, more than 0.4. And you look at the shape of SO2, there are some lone pairs on sulfur atom. The lone pairs will create a partial negative area around the sulfur atom, making this molecule also polar. Then, if I look at CO2 number 5, CO2 number 5. Carbon has electronic value of 2.55. Oxygen has 3.44. The difference in electronegativity is going to be 3.44 minus 2.55. When we subtract, we're going to have, for this, 3.44 minus 2.55 will give around 0.89. Okay, 0.89, about that, which was a big value. Also a big value, yes. Comparable is a big value. That will suggest that this molecule may be polar. But we're going to look at the structure of CO2, the geometry, and see whether it's going to be polar or not. As we said, that a molecule can have a electronic value that is very large, more than 0.4, and still at the end will not be polar, depending on the shape. Let's look at the shape of CO2. As we have done shape, CO2 has a double bond, linear shape between carbon and another oxygen atom. If I shift this bond as electron this side, I'm going to have oxygen here being partially negative, and this oxygen move this electron up being partially negative, and carbon at the center being partially positive. Look at the CO2, you see two atoms of the same kind, the same electronegativity facing each other. And the carbon atom at the center has no lone pair. I come again. Look at CO2. You see two similar atoms opposing themselves, having the same charge. And then the central atom, most importantly, has no lone pair. That means the dipole moment of these two atoms will cancel each other. This molecule is symmetrical. You can picture it this way: equal half, CO and CO. The central atom having no lone pair. The negative charge here will cancel this. So we'll now say that this molecule, the dipole moment, have cancelled each other. Even though the CO bond, the difference gave us a light value, is negative, but the molecule as a whole, CO2, is a non-polar molecule because the dipole moments cancel each other. Now, let's look at number 6, methane. If I look at methane, CH4, let's look at the difference in the methane. This is 2.55 for carbon. Hydrogen is 2.2. So difference in electronegativity is going to be 2.55 minus 2.2, giving us 0.35. The value we have calculated is too low for a molecule to be polar because it's not even up to 0.4 that we predicted. So this molecule is likely to be non-polar. Even if we look at the shape of methane, we are done bonding. If you go to the shape of methane, you see that methane has a kind of tetrahedral shape, whereby the central atom has no lone pair, just like in CO2, while the central atom has no lone pair, similar, no lone pair. And then opposite the central atom, either from this side or this side, have the same atoms opposing themselves. And the electronegative values will cancel themselves because it's a symmetrical molecule. The central atom has no lone pair, and you have opposing similar atoms on any of the side, either north, east, or south, west. So methane is symmetrical, just like CO2. So both are non-polar molecules. At least with that, you can predict the polarity of some simple covalent molecules. The next bond property we're going to look at is bond dissociation energy. We can represent it with a symbol capital D. So what is bond dissociation? You know that the word dissociation means to break, to separate. The energy required to separate. To separate what? So say this is the energy supplied to a gaseous molecule to separate two of its atoms. The energy supplied to a gaseous molecule to separate two of its atoms. For example, if I look at a molecule like HCl, which could be gaseous, It's applied to this molecule to separate the atoms. Remember that in HCl there's a covalent bond between hydrogen and chlorine into hydrogen and chlorine atom. It's now called the bond dissociation energy. Energy supplied to a gaseous molecule to separate two of its atoms. So you can still consider maybe another molecule let me say HBr in gaseous state. The energy required to separate the atoms into hydrogen and bromine atoms is its bond dissociation energy. Now in chemistry, bond dissociation energy is very important in thermodynamics or in thermochemistry because it can help us to calculate the enthalpy of a reaction. What is the enthalpy? Enthalpy is nothing but the heat of reaction or the heat change of a reaction at constant pressure. That's what we call enthalpy. And there are different kinds of enthalpies. We have enthalpy of formation, enthalpy of combustion, enthalpy of neutralization. But in this calculation, we're going to focus on enthalpy of formation and enthalpy of combustion. So if you want to calculate the enthalpy or the heat change during a chemical reaction using the bond dissociation energy, you use the formula enthalpy equal to D energy of reactant. That means dissociation energy of the reactants minus dissociation energy of the product. That D means the bond dissociation energy. So dissociation energy of the reactants, I did not say product, reactants minus that of the products. That will give us the enthalpy of either formation or enthalpy of combustion. So let's take a few examples on this. Now let's look at the equation on the whiteboard. We have an equation there between hydrogen molecule and chlorine giving us two molecules of HCl. Have delta HF, that I said delta H means enthalpy and that F means formation. On top you have theta. That theta means standard enthalpy of formation. Question mark on it, that means we're looking for the enthalpy of formation. Question says calculate the enthalpy or heat of formation of HCl using the given data. And then you have this, we have the dissociation energy of the molecules given to us of I should write D and D. So we have the bond dissociation energy. They are required to break the bond in hydrogen molecule. This hydrogen, two atoms there. We need 436 kilojoule per mole. The bond energy required to break two atoms in chlorine to two atoms a molecule to give you two atoms is 243 kilojoule per mole. Then the bond energy required to break the hydrogen and chlorine atom here into hydrogen and chlorine free atoms is 431 kilojoule per mole. So we are asked to use this information to calculate the enthalpy or the heat of formation. As I told you, you can calculate the enthalpy of reaction using the bond dissociation energy. And I gave you a formula that says enthalpy of reaction is equal to dissociation energy of reactants minus that of products. Before I go on to solve this problem, I have to ask myself, what is formation? What is the meaning of heat of formation? Heat of formation is the enthalpy change. The formation of HCl. When 1 mole of HCl, 1 mole of a compound, not only HCl, 1 mole of any compound, 1 mole, the word there is a mole, is formed from its constituent elements. Now, from this equation, HCl have been formed from hydrogen and chlorine, which are the constituent elements. But the number of moles of HCl here is not 1, but rather 2. So our focus is what is being produced is HCl. So we should have 1 mole here, not 2 moles. So what do we do, or how do we go about it? We have to, before we solve, to make it easier for us, we have to reduce this to 1 mole. How to reduce this to 1 mole? We'll divide the coefficient of every substance here with 2 so that it can be 1. So the coefficient of hydrogen here is 1. So divide by 2, you have half hydrogen plus half chlorine, then HCl. Now here we can now talk about heat of formation, because we're not talking about getting 1 mole of HCl from the constituent elements. Had it been that the equation already gave us 1 mole, we are going ahead to calculate. But since we have 2 moles here, we have to reduce everything to get 1 mole, because we are talking about producing heat evolve when you produce 1 mole of HCl. Now we'll go ahead. The equation we need is, we say enthalpy of reaction or formation given by bond energy of reactants minus bond energy of products. Okay, I can say summation. This symbol means summation, just like E, epsilon. Summation, the total of the bond energy of reactants minus the total or summation of bond energy of reactants. So having done that, I think we'll move up and then solve to make it clearer. So having done that, we now have the equation we're working with, not the former previous one. The reactants here are hydrogen and chlorine. Before we start calculating how to show the bond in this, in hydrogen, there's a single bond. I have half mole in front. In chlorine, as you can you're seeing even the hint is there for you. Also single bond in chlorine molecule. You can see that. Then in HCl, there's a single bond also in HCl. So we're going to find the total energy or bond energy of reactants. So the first reactant here is hydrogen, only 1 hydrogen bond. So hydrogen to hydrogen, the bond energy of hydrogen to hydrogen bond is 436. I'll now multiply 436 by half. How do I get the half? The bond energy of hydrogen to break hydrogen bond, and there's only 1 hydrogen bond, is 436. Multiply by half, because the number of moles in front is half. Then plus half times the bond energy of chlorine. In chlorine, there's only 1 bond we're considering, and there's number of moles in front is half. So the bond energy for chlorine molecule is 243. Multiply by 243. So when we solve this, we'll now be having 218 plus 1 to, I think around 1 to 1.5, about that. If you add the 2 of them together, we have 339.5 kilojoules. So this is the bond energy for the reactants. Having done that, so you add the bond energy of this and this. There's only 1 bond of hydrogen. Multiply by the stoichiometric number of moles, half in front. The high chlorine, pick it from the data, multiply by half. When you have done that, you have gotten this one. Then look for the total bond energy of products. So summation of bond energy of products. There's only 1 product there, and that product is HCl. So now I've just find the bond energy of HCl. There's nothing in front, is 1 mole. Remember that is formation we're considering. So the bond energy of HCl given to us already, I'll clean it, but I'll pick it from the question. The bond energy of HCl is 431 kilojoules. So it's 431 kilojoules given to you. So multiply with nothing because you have only 1 mole. Then the enthalpy of formation is now the difference between the bond energy of the reactants and products. So the reactants 339.5 minus product 431. That gives the final answer, which is minus 91.5 kilojoule per mole. Minus 91.5 kilojoule per mole. We take another question. Still on bond energy or enthalpy formation, we're taking example 2 that says calculate the enthalpy formation of dinitrogen tetrafluoride N2F4. 0. Dinitrogen tetrafluoride N2F4 with the reaction below. So we have a nitrogen molecule, 1 number in front is a molecule, reacting with 2 molecules of fluorine to produce 1 molecule of the compound N2F4, dinitrogen tetrafluoride. Now let's look at this question. We'll ask ourselves, just like we did in HCl, we're still looking for enthalpy of formation. What is being formed there? The product, which is this compound N2F4. We are lucky in this question. Why did I say you're lucky? Because in this question, the bonds have been drawn already for you. So the bond, you're not going to open the structure yourself. You just do the calculation only that they need from you. Now look at this question. This question is very interesting. Very interesting. Then are we going to divide the as we did in HSM, divided by 2 all true? No. Why do we divide by 2 in HSM? Because enter formation deals with only one more of the compound. In the previous question that we solved, there was 2 in front of HCl, so we have to reduce this into 1 by dividing by 2 or 2. But in this particular question, we only have one more of the compound formed. So we'll go ahead with calculation because our interest is in forming this compound. One more of it will give it to the equation. Had it been that we have 2 here or 3 here, we divided everything by the number we are seeing there to make this place one more. Now let's go ahead. We'll now find the enthalpy of the reactant, summation of enthalpy of, summation of the bond energy of the reactant, D of reactant, summation. The reactants are nitrogen molecule, so now I say bond energy D of N to N, nitrogen triple bond, plus adding this also, now I say bond energy of fluorine to fluorine molecule, multiplied by the coefficient, the symmetry, which is 2. There's 2 in front, so multiply by 2. But this one multiply with nothing because there's only 1 in front. We're going to add the 2 bond energy. So for nitrogen triple bond, look at the values given to you. You don't get confused. This is nitrogen single bond. This is different from this. The bond energy of nitrogen single bond, look at the triple bond under 946, not 159. So the bond energy of nitrogen triple bond is 946. Then plus 2 times that of fluorine molecule, which is given to us, is not provided. We have to get it from literature. The bond energy of fluorine molecule should be given to us, let's get it, 158.9. So the bond energy recorded of fluorine molecule is 158.8. So that's the value, kilojoule per mole. So it's an omission. So we have to bring it in, 158.8. So when we add this together, we'll multiply 158.8 by 2 and add it to 946. I'll be getting 1263.6. 1263.6 kilojoule. That's the bond energy of the reactant, total bond energy of the reactant. So having done that, I can clean the upper side and then calculate the bond energy of the product. I will have only one product here. So the bond energy of the product. Now, we'll now look at the product. What kind of bonds do you have in product? In the product, you have nitrogen fluorine bond. How many times does nitrogen fluorine bond occur? NF bond, NF bond, NF bond, NF bond. So 1, 2, 3, 4. So there are 4 NF. So we'll now write 4 multiplied by DNF. Since there are 4 of this bond in this molecule. 4 times that. Then, is it the only bond that is present there? No. We still have nitrogen-nitrogen bond. So we'll now say plus the bond energy of nitrogen, and there's only one of nitrogen-nitrogen bond. So we have to multiply by 4. I have 4 of NF bond, nitrogen fluorine, and then only one of nitrogen-nitrogen single bond. Remember, it's different from this bond. So we'll now solve, substitute. The nitrogen fluorine bond is given to us in the data as 272 plus the nitrogen bond, single bond, is 159. We'll solve this out. When we solve it, we're going to have 2034 kilojoules. 2034 kilojoules as well as our bond energy, total bond energy of the product. Now, since we're looking for the heat of formation now, we now have enthalpy of formation. Will now become total of bond energy of reactants minus the summation of bond energy of products. The bond energy of reactants is What the reactant again? Okay, 1263.6. The product 2034. When we subtract, we have a final answer. And the final answer is negative 770, 770.4 kilojoule per mole at the heat of formation of the substance. You see, very easy. We take another example, but this time around from heat of combustion. So let's look at the question on the board. The question is on combustion. And as we learned in chemical reactions, types of chemical reactions, combustion is the reaction whereby a substance burns in oxygen. So as you can see in that equation, ethene, C2H4, was burned in 3 moles of oxygen, that is combustion, to give you 2 moles of carbon dioxide and 2 moles of water. And we're given the enthalpy of combustion, a different kind of enthalpy. Enthalpy comp or combustion of 18 as 132523 minus 1323 kilojoule per mole minus 1323 kilojoule per mole. And we're asked to estimate the bond dissociation energy of carbon to carbon double bond. So in this question, we are not looking for the enthalpy of reaction, but we're looking for the bond energy in one of the reactants in 18. I repeat, in this question, we're given the enthalpy of reaction. We're not looking for the enthalpy, but we're looking for the bond energy in one of the reactants in 18. So this question, we're going to see solved by the same formula, by using bond energy of reactants minus the total of bond energy in the products. But before we go ahead, although this should be done under thermodynamics, you have to understand what is meant by enthalpy of combustion. Enthalpy of combustion is different from enthalpy of formation, but they have something in common. What they have in common is that enthalpy normally involves 1 mole of the substance concerned. In formation, we are talking about the heat or the enthalpy change when 1 mole of a compound, you only have 1 product, you can't have 2 products. 1 mole of a compound is formed from each element, the element that make up that compound. For instance, if I want to talk about the enthalpy of formation of water will be on the product side. And then I'm talking about how I will get 1 mole of water by combining the elements in water, which is hydrogen and of course oxygen. To have 1 mole of water here, this is 1 atom, I have to break this one, multiply this one by half. Because half times 2 give you 1. So the energy change that occurs when I form water, 1 mole from the constituent element is the enthalpy of formation, which I've discussed already. But this hour, or minute, we're looking at the enthalpy of combustion. Combustion doesn't have to do with the product. Combustion deals with the reactant. So what is the enthalpy of combustion? Enthalpy of combustion is nothing but the amount of heat liberated, because combustion is an exothermic reaction, liberated when 1 mole of a compound burns completely in oxygen. So it's not a product we're talking about now, we're talking about a reactant. The amount of heat obtained when 1 mole, which compound we're talking about here? 18, burning in oxygen. How many moles of 18? 1 mole of 18. So the amount of heat liberated by burning 1 mole of 18 inside oxygen is this amount of heat, 1323 kilojoules of heat energy was liberated. Someone may ask, what if I had 2 moles here, or 3 moles, or 10 moles here? Will this stand for the enthalpy of combustion? No. If I have 10 moles here, that means I'll divide all through by 10. So that I will have only 1 mole of the substance burning in oxygen. That is the enthalpy of combustion. That is, by the way. Our interest here is not to calculate enthalpy of combustion, although we have understood what it means. 1 mole, combustion refers to a reactant. 1 mole of it burning in oxygen. Formation refers to a product formed from the constituent elements. But it follows the same process. Now, before we go ahead, the first thing we have to do is to draw the bonds inside, because there was no structure given to us. In 18, there's a double bond. It's an alkene, we know that. In 18, double bond in 18 between the 2 carbon atoms. Oxygen, we have done covalent bond in oxygen. Oxygen contains a double bond between the 2 atoms. So that's the bond in oxygen. And there are 3 atoms in front, 3 moles in front, right? Sorry. Then in CO2 has a linear shape where carbon is at the center. That is CO2. That's the shape of CO2. Double bond between two adjacent carbon, between carbon and the adjacent oxygen atom on both sides. And there's also two moles in front. That is the two. In water molecule, water has sort of hydrogen linked to oxygen and linked to. So there is two hydroxyl bond, OH bond in water, HH2O, and then two molecules form in water. So you have to open the structures and write out the bonds before you start the calculation. So having done that, we can now start calculating without waste of time. So we have to write the board and then make use of a part of the board. So we now find the enthalpy, the summation of dissociation energy of the reactants. They call it R, so I'm not write so much. That R stands for reactants. The reactants include this, and they're going to add the bond energy of this and that. Let's start with this one. I'm having CH bond here. CH. How many times did the CH bond occur? This is 1, 2, 3, and then 4. So there are 4 carbon to hydrogen single bond in 18. 1, 2, 3, 4. So now I have 4 times dissociation energy of carbon hydrogen bond. So is that the only bond in 18? No. I still have carbon to carbon double bond. Carbon to carbon double bond, C to C. It only occurred once. So and I say plus so energy of carbon to carbon double bond. You see, that takes care of 18. We go to oxygen. Look at oxygen. We have oxygen in the oxygen molecule. There is a double bond between two oxygen, but there are 3 moles. So now I say plus 3, the energy of oxygen to oxygen double bond. So we're going to add all this together from the data. The energy of carbon to carbon double bond, single bond, is 414. And I write 4 into 414 plus the energy of carbon to carbon double bond was not given to us because it is what we are asked to find. We're clearly that what we're asked to find. We have to find this. So we're asked to find that carbon to carbon double bond. So I can call it S, unknown. There's nothing in front. It's only one of the bond. If there were 2, I would have said 2 times S. Then plus 3 times that of oxygen. That becomes 3 into the energy of oxygen is 498. That is it. So when I multiply everything together and add them, I'll have 4 times 414 plus 3 times 19498. So we get the correct answer without waste of time. 4 times 414, that gives us 1656. 3 times 498, so that gives us 1494. So if I add together, okay, let's just write it out first. It will be 1656 plus S plus, multiply that one, I'll have 1494. So I can clean up the reactant. I'm done with this side. So if I add these two, collecting reactants, 1656 plus 1494, that give me 3150. 3150 when you add these two, then plus S. So this is the bond energy of the reactants. Done. Then the products, as we said, clean it up. The products include 2 oxygen to oxygen CO2 bond, and then this is water. So now find the bond energy of the product. They call it DP. Going to the product, in CO2, there is carbon to oxygen double bond, and they give us the energy as 803. Carbon to oxygen double bond, how many times they occur? It occurs 2 times CO and another CO. So there are 2 carbon to oxygen double bond in CO2. They multiply by these 2, that becomes 4. So I now write 4 multiply D oxygen to carbon double bond. I repeat myself. In CO2, we have what they gave you is the bond energy for that bond energy that break the bond between carbon to oxygen double bond. And how many of these are in CO2? There are 2 of them, here and there. That is 2. Multiply by 2, then 4 times that. Then going to water. In water, we have the oxygen to hydrogen bond occurring 2 times. 1, 1, that is 2. And 2 times this to gives you 4. So now I have zero energy of hydrogen 4, okay, 4 times the zero energy of oxygen to hydrogen single bond. So you know, understand what I did. So having done that, we'll make a substitution that becomes, I can clean up this side and use it. That becomes 4 times the energy of oxygen to carbon double bond, which is 8O3, plus the energy of 4 times oxygen to hydrogen bond, that is 464. So use a calculator and press, get the answer. We now have 4 times 803 plus let me get it right. Write it down. Wow, okay, we'll multiply 4 times 803, give us 3212. 3212 plus 4 times 464, 1856. If you add them together, we'll have our energy plus 3212 plus 1856. That gives us 5068 kilojoules. So this is the bond energy of the product, 5068. The reactant, 3150 plus S. S is unknown, that of carbon-carbon double bond we're looking for. So having understood that, we can go ahead, wipe the upper part and then work over there. Then to solve it, we know that the enthalpy change will become the summation of bond energy of reactants minus that of the product. I remember that the enthalpy change, the heat of reaction for the combustion is given to us in the equation, minus 1323. So replace this with negative 1323 equal to the summation of the bond energy of the reactant. We got it as 3150 plus S, which we're looking for, then minus that of the product, 5068. Having done that, we now collect like terms, making the solve the formula. So we're going to cross everything we have on the right hand side to the left hand side. So S becomes negative 1323, cross over, negative 3150, moving over, plus 5068. So when we solve this out, our final answer will now become 595 kilojoule per mole. 595. So this is the bond energy for carbon to carbon double bond in 18, which we are asked to find. That is 595 positive value kilojoule per mole as our answer. So having seen how to calculate, having seen what is meant by bond energy, and how to calculate bond energy using how to calculate enthalpy of reaction, formation, and combustion using bond energy, we are now going over to the Born-Haber cycle. In my first video, I promised that I made a comment because there was a kind of have a technical issue whereby the video wasn't covering the board partially. So when I did the Born-Haber cycle, part of the board was cut off. And I made a promise that I'm going to repeat the Born-Haber cycle in the next video. So having discussed some of the bond properties, so let us look at a very important thermodynamic cycle called the Born-Haber cycle. So, and then look at repeat the calculations within the first video and make it more clear. Okay, now we're going to look at a very important thermodynamic cycle called the Born-Haber cycle. So the Born-Haber circle is the thermodynamic circle used to calculate the lattice energy of an ionic compound. Lattice energy, which is a property of ionic compound, is the energy evolved or given out when 1 mole of ionic compound is formed from its constituent gaseous ions. Repeat, lattice energy, the energy evolved when 1 mole of an ionic compound is formed from its constituent gaseous ions. The circle is based on Hens' law of constant heat summation. Hens' law of constant heat summation, SUMMATION. This law states that the enthalpy change of a reaction is the sum of the enthalpy changes of the reactions that make up the given reaction. So what this Hens law tells us is that a reaction can take place, or a reaction can involve so many steps. So the heat change of the main reaction is the sum of the heat changes of all the reactions that depend on the main reaction. That's the Hens law of constant heat summation. So let's look at the process of Born-Haber circle and then see how to go about it. So in the Born-Haber circle, let us consider an ionic compound, a metallic chloride. For example, sodium chloride. This compound is formed. The first step what to consider is formation, which we discussed a few minutes ago. To form sodium chloride from its constituent elements, so the equation will go to sodium plus chlorine, giving us sodium chloride. We need the enthalpy of formation to do that. To form 1 mole of sodium from 1 mole of sodium chloride from the constituent atoms, we need the enthalpy of formation. And remember that in formation, we're talking about 1 mole of the compound. Balance the equation, we have 1 mole here, 1 mole. But for chlorine, we have 1 atom there, and we have 2. We have to put half here to balance it. So having done that, the metal undergoes 2 stages. The metal is in solid state. The first stage it undergoes in the Born-Haber circle is what called sublimation. Sublimation, that is turning from solid to gas. So you now have NaG going from solid state to gaseous state. It needs the enthalpy of sublimation, which is the positive enthalpy. So that's the first stage. The next stage the metal undergoes is what we call ionization, after it has lost electrons. So when you lose electron, it forms sodium ion in the gaseous phase. It needs the ionization energy, which is also a positive enthalpy. So in the Born-Haber circle, the metal undergoes 2 stages, which we have itemized. 1, sublimation. Number 2, ionization. Now going to the non-metal. The non-metal, which is chlorine, also undergoes 2 stages. First of all, the molecule will break into its atoms to give you free gaseous atoms. We need the dissociation energy. Remember, when we did the bond property of covalent molecules, we mentioned this energy dissociation. We mentioned also formation. Then the next step, this gaseous atom produced is now undergo to call electron affinity. Being a non-metal gains energy. The energy gains is called electron affinity. So electron affinity is negative, while energy of dissociation is positive. So as I repeat myself, the metal undergoes 2 stages. It sublimes to its gaseous atom. The gaseous atom loses energy to ionize. The non-metal dissociates into free atom. Then the free gaseous atom gains energy to form a negative ion in the gaseous state. You see that? So having done that, the next thing now is these 2 ions can still combine and form this. You see? The 2 ions form, the sodium ion can combine with the chloride ion to give us, let me push this a little bit up for you to see it. Sodium atom, chloride ion. So these two can still combine to give us the product form over there. And what energy is required, or what energy is required to form an ion from its gaseous atoms? We require the lattice energy. You see that this reaction looks small like the one on top, but they're not the same. The energy required to form 1 mole of a compound from the constituent atoms is energy of formation, but energy required to form 1 mole of any compound from the gaseous ions is the lattice energy. So you see that so much energy are involved in this step. The major reaction here is the formation reaction, forming sodium chloride. But all the main reaction, all these other reactions are embedded in the main reaction. So based on Hence law of constant heat summation, it means that the enthalpy of the main reaction, the heat energy released in the main reaction, will now be equal to the sum of every other reaction that depended on it. So we now become the enthalpy of sublimation plus, which is the energy, ionization energy plus dissociation energy plus electron affinity plus lattice energy. So you see that 5 energies are summed up to give us the enthalpy of formation according to the Born-Haber cycle. You see, that is a very interesting aspect of thermodynamics, which is also involved in bonding, ionic bonding. Now, having done that, we also mentioned in the previous video, though it didn't get us clear, that if the non-metal is diatomic, or it's a common example like chlorine, bromine, iodine, fluorine, we modify this formula. So we now say the enthalpy formation becomes the energy of sublimation plus ionization energy. You now divide the dissociation energy by 2. Because when you dissociate this, you're going to produce 2 free atoms. But in the Born-Haber cycle, we are talking about producing only 1 atom of chlorine. So the Born's energy, normally they're going to give you will be 2 atoms. But we are concerned with producing only 1 mole of the atom in the Born-Haber. So that will have divided by 2. So plus EA plus L. So let me ask, what if the element is triatomic? They have divided by 3. So having done that, let's now look at some key examples. So let's look at some examples now. So look at the question on the board that says determine the lattice energy of sodium bromide. The following data: heat of formation of sodium fluoride, should be NaBr, sodium bromide. This is bromine, please. Sodium bromide, NaBr, is minus 569 kilojoule per mole. Heat of sublimation of sodium equal to 109 kilojoule per mole. Dissociation energy of bromine molecule 154.8 kilojoule per mole. Ionization energy of sodium 496 kilojoule per mole. Electron affinity of fluorine minus 33 kilojoule per mole. So from our Born-Haber cycle, we have the relationship that says enthalpy of formation again by the other enthalpies added together. Enthalpy of sublimation plus ionization energy plus the bond dissociation energy of bromine. I use the molecule, so divided by 2 plus, meaning how many of it? We have formation, enthalpy formation, sublimation, we mentioned that, dissociation, ionization plus electron affinity, and of course the lattice energy which you're looking for. So make a substitution. The enthalpy of formation is minus 569 up there. The enthalpy of sublimation of sodium 109. The initial energy of sodium given to us somewhere 496. The dissociation energy, which is given to us as 154.8, because the molecule divided by 2 plus electron affinity is minus 333, then plus L. So we have that. So we're going to solve this to get our final answer. So when we solve, let's wipe the upper side and then proceed to solve. So now I have minus 5969 equal to 109 plus 496. Divide this, that gives us plus 72.4 if I'm right. So let me check it very well. 77.4. Divide 154.8 by 2 minus 333 plus L. So we can now collect all the terms. If we add, we're going to have minus 569. Everything here added. 109 plus 496 plus 77.4 minus 333 will give us 349.4. Now 349.4, then plus L. Now make L the solve the formula. L will now become, crossing this one to that side, becomes minus 569, then minus 349.4. So finally, our final answer will become minus or negative 918.4 kilojoule per mole. So this is the lattice energy of sodium bromide based on the calculation. We take a second question. So go to a second question, which says, before we go to the second question, we have to make a little correction on the first one we solved on lattice energy. Not that there was no mistake, but the question was on to calculate the lattice energy of sodium fluoride, NaF, please. If you're copying it down, it's a sodium fluoride, not sodium bromide, NaF. So that is the right thing that should be here. To calculate lattice energy of sodium fluoride, heat of formation of, now what should be here? There should be NaF, not NaBr. So heat of formation of sodium fluoride was given to you there, and that should be minus 569 kilojoule per mole. The next one should have been heat of sublimation of sodium. That one is no problem. The third one is dissociation energy of fluorine, F2. That one should be in that form equation, F2, not Br2. And then I think every other thing follows. Then electron affinity also given to us here. So that one was electron affinity of fluorine of F, not Br. So we change that of F, which should be minus 333 kilojoule per mole. The calculation follow the same process. Everything is correct except for made a mistake where you see bromine in that question, replace it with a fluorine F, F2F. So they remain the same, and then the question shows lattice energy of NaF. Calculation is correct. So now let's look at this problem now. It says calculate the electron affinity of bromine. This time around we're using sodium bromide now. The same formula I gave to you. We have an enthalpy of formation begin by enthalpy of sublimation plus ionization energy plus we can say dissociation energy. Can divide by 2 because this is a diatomic molecule. You can see 2 there as we did in the previous one. Then plus electron affinity, there should be 5. Then plus lattice energy. But this time around, we are not looking for the lattice energy. We're looking for the electron affinity. So they still the same process. Let's make a substitution. The enthalpy of formation is minus 359. So minus 359.9. The sublimation energy for sodium is here 109. The initial energy of sodium is 490. energy of a bromine molecule 192.4 divided by 2 because it's the atomic, as I did for the other one, fluorine, plus electron affinity, which you are looking for. Good. Then plus lattice energy. That energy is given to us as minus 736.1. So, having obtained these values, I can now solve y the upper side and then continue my solution from up. So, I can bring this thing up. That becomes minus 359.9, 109 plus 490 plus 192.4 over 2 plus EA. Then minus will cancel plus, giving us 736.1. Minus 359.9. 109 plus this will give you 599 plus, you divide, I give you 996.2 plus EA, then minus 736.1. So to get my electron affinity, I'll collect like terms. So my EA becomes equal to minus 359.9 crossover minus 599 crossover minus 96.2 crossing over becomes plus 736.1. So solving this out, electron affinity will now be equal to final answer 325 kilojoule per mole as our final answer to that question. So in this aspect, we're going to discuss hybridization of molecules, simple molecules, which is a development of the valence bond theory. So we have discussed the valence bond theory, but our type won't permit us. We may not go into valence bond theory. Maybe for another video we can do that. So we're going to discuss hybridization, missing of atomic orbitals. And in chemistry, there are different types of hybridization. We have the sp, have the sp2, have the sp3, and so on. We'll discuss the geometry of molecules. We'll discuss the shape of molecules. Let's start with the linear geometry. Molecules that have linear shape, like CO2 or beryllium dichloride, beryllium hydride. What kind of hybridization would they have? Linear molecules normally have sp hybridization. So let's use an example to demonstrate. Let's use beryllium chloride dichloride to demonstrate this. To demonstrate the linear shaped molecule, because the central atom has no lone pair, it's bonded to two atoms, as we discussed in the other section of the video. Before we do hybridization, we have to look for the central atom here. The central atom there is beryllium, the one that has only one atom. The central element is beryllium. Right, the electronic configuration in the orbital form, the sub energy levels, that is 1s2, 2s2, that is the EC of beryllium. Having done that, we're now going to draw the orbital diagram of beryllium. We draw the orbital boxes, beryllium 1s, 2 electrons in the s orbital, and then 2s, 2 electrons in the p orbital. So this electronic configuration you have drawn is called the ground state. The ground state electronic structure of beryllium. Before beryllium will hybridize with chlorine, it must have 2 unpaired electrons with the normal valency of beryllium. So electrons here are all paired. So beryllium will undergo what's called excitation, a process whereby the atom absorbs photons of light energy. An electron in the 2s shell will now move to the 2p shell, so that beryllium will have 2 unpaired electrons, maintaining its usual valency. So let's now draw, this is 1s. We're now drawing the electronic configuration of the beryllium in excited state. This is the ground state, the normal state. So we now draw the next orbital, which is the 2p orbital, which is divided into 2ps, 2py, and 2pz. So we have 2 electrons here. One electron in the 2s will now be shifted Why not the one in the 1s? The 1s orbital is close to the nucleus, so the attractive force there is very strong. So it should be the 2s in the L shell should be removed. Should moved to the 2ps. So you now have two unpaired electrons, beryllium in the ground state, beryllium in the excited state. We now want to bring in chlorine atoms. So two chlorine atoms will now come in to mix with the beryllium orbitals. So how is it going to be? So in beryllium chloride, the two chlorine atoms will bring one electron each. So let's see what will happen here. Now have 2s, now have 2p, 2ps, 2py, 2pz, empty, one here. So the two chlorine atoms, one from here, will now move into this place. This from chlorine, this electron, and that chlorine electron enters here. So when you see that, what kind of hybridization scheme do you have? To hybridize, for beryllium to hybridize with chlorine, you use one of the s orbital and one of the p orbital. We now call this sp hybridization in beryllium chloride. So now we say that linear molecules have sp hybridization. We take another example. So we look at another molecule that has the niche shape, trigonal planar shape, boron trifluoride, where the central atom has no lone pair bonded to 3 atoms. So trigonal planar molecules normally have sp2 hybridization scheme. So the central atom here is boron. Let us write the electronic configuration of boron with 5 electrons, 1s2, 2s2, 2p1. If I draw the ground state, GS means ground state, orbital diagram of boron, I'll have 1s, 2, 2s, 2, electrons in opposite direction according to Pauli's principle, and then 2p, s, 2p, y, 2p, z. So one electron entering there. So you can see that. But boron cannot be undergo hybridization with boron orbital cannot be mixed with fluorine orbitals in this form because we need 3 fluorine electrons. And then you know that boron is in group 3. Going by the normal electronic configuration, 2, 3. Normally has valency of 3. So you should have 3 unpaired electrons before you start hybridizing. So we'll talk about the excited state before we'll talk about hybridization, whereby an electron in the 2s orbital will absorb light energy and be promoted to an empty 2p orbital. So we can sort it out. So we have 2 electrons. So 1 electron from the 2s will absorb energy and then move into one of the empty 2p. You can see that. So you cannot enter here. You have to look for an empty one enter because it must be in accordance to Hund's rule of multiple multiplicity. Let's say that for such energy level, electron will go singly before they start pairing. Now, we now have boron trifluoride. How is the hybridization scheme now? So we have 1s, then 2s. 1 electron. Okay, let's just draw the boron first, the starting state first, before we now talk about the hybridization scheme. Or before bring the electron from fluorine. So 1 fluorine electron will enter here. This from fluorine, another one, another one. So you now have this. So the hybridization scheme in fluorine, in boron trifluoride, I have used one of the s orbitals, that is the 2s, and used 2 of the p's, that is 2p. That gives us what's called sp2 hybridization scheme in boron trifluoride. Move to another example. So look at another molecule on the whiteboard, ammonia. Ammonia has trigonal pyramidal shape. So molecules that have trigonal pyramidal shape, like ammonia or phosphine we discussed today, tend to have sp3 hybridization pattern. Let's see how true it is. Look at nitrogen, 7. Write the electronic configuration, 1s2, 2s2, 2p3. Let's draw the electronic configuration of the atomic structure orbital bus. 1s, 2, 2s, also 2, 2p also having 3. 1, 2, 3. 2ps, 2py, 2pz. So this is the ground state electronic structure of orbital diagram of a nitrogen. Question is this: will the electron in the 2s be promoted to another orbital? Or which orbital will we go to? We go to the next orbital that come up with 3s. In ammonia, nitrogen does not hybridize with the 3s orbital, because look at it. There's only 3 unpaired electrons. And the normal oxidation state or valency of nitrogen in hydrides is 3. So it already has maintained 3 unpaired electrons. So there's no need for excitation of an atom again here, because it already has 3 unpaired, meaning that I maintain the usual valency. Then to form ammonia, we now have NH3. Each of the nitrogen atoms will now bring electrons. The electron, where would they feel? Let's see where they will go to. So the only space they can enter are the p2p orbitals. So what do we call it? You have 1 of nitrogen here, hydrogen, 1 from hydrogen, 1 from nitrogen, filling all this space. Now, what do we call this scheme? Do we just call it P3 hybridization scheme? No. You see, we count this one first. This electron here is the lone pair on nitrogen atom. If you draw the shape of ammonia, remember the shape, trigonal pyramidal, there's a lone pair of electron on top of nitrogen. So that 2 electron here is the lone pair that is on the 2s. So we'll include this s, the lone pair, plus 3 of the p's. That gives us sp3 hybridization in ammonia. Another illustration on the board is water having V shape. So in water, we say V or angular shape is also sp3, just like ammonia. Let's see why. The central atom there is oxygen. Let us write the electronic configuration: 1s2, 2s2, 2p4. Add everything together, that is it. Then the orbital diagram of oxygen: 1s has 2 electrons, 2s has 2 electrons, and then 2p has 1, 2, 1, 2, 3, and then what? 4. You see, 2ps, 2py, 2pz. Now, does the high oxygen undergo hybridization on the ground in the ground stage, just like nitrogen did its own? Yes, because in oxygen, the valence of oxygen is normally 2 cis, and there are 2 unpaired already for bonding. So there's no promotion to any other higher shell. So we're going to bring electron from 2 hydrogen to fill out this space. So now water, now have this 1s 2 electrons, 2s under 2 electrons. They're coming to 2p. The first 2p is already paired. So that means the 2 electrons from hydrogen will enter the 2pz and the 2py and 2pz to pair up. So now, what do we call this scheme? This is sp3. Why not p2 only? We use p2. Why sp3? When we did the bonding in water, if you look at the structure of water, the V shape of water, you see that the oxygen atom of water has 2 lone pairs on it. That's why it's V shape. So the 2 lone pairs, what account for the 2 lone pairs? So these 2s electrons is a lone pair. The 2ps is another lone pair. So they're counted in hybridization. So S, one of the S, and 3 of the P's. Out of the 3 P's, 2 bonding pairs and 1 lone pair. So look at that molecule on the board: phosphorus pentafluoride. That has the central molecule phosphorus with no lone pair electron on it, and then bonded to 5 atoms. And such molecule we say it possess trigonal pyramidal shape. So such molecules should have what called sp3 hybridization scheme. sp3. So let's find out. Let us write the electronic configuration of phosphorus using the subshells. 1s2, 2s2, 2p6, 3s2, that is 10, 12, 10, 12, and then 3p1. You add it. This is 4, 10, 12, okay, 3p3. So let's draw the beta diagram. I may not be interested in drawing all this because this one represents a noble gas. 4, 10, that is neon. So let's draw these two. Have 3s, that is it, and then 3p. Being the p submit level, we're going to share electrons in accordance to Horn's rule, one after the other. So 3ps takes 1, 3py, because p orbital automatically go 1 by 1. Whether it's 3p or 2p, that the process takes 1. So I remove this one because this one is the field in that is a not neon removed. So even though if you draw it, there's no problem. It's still okay. So don't feel you can remove it. I should remove it. I just want to make it easy and faster. I just draw the last two orbitals. Then this is going to give us which orbital. Now let's look at it very well and see whether there are error there. 12, 15. So look at the structure again. Phosphorus. There are 3 unpaired electrons in phosphorus. In phosphorus 5 chloride, phosphorus maintains a valency of 5. So we should have 5 unpaired electrons. So that means there should be an excited state. So in excited state, the next orbital that should come in after the 3p, going to use in this orbital is not the 4s, no. Phosphorus uses not the 4s, uses the 3d in hybridization. So the next orbital is now the 3d drawn, and 3d, you know, the subunit level is also divided into 5. 1, 2, 3, 4, 5 boxes in 3d, and then 3 in boxes in 3p. So let's see what happens. That means one of the electrons from the 3s will be promoted to an empty 3d, since these ones are already single. So now I have 2 electrons here, 1 here, 1 here, 1 there. And 1 electron leaves here and moves to an empty 3d orbital. So you see the way it goes. Then for us to have PCl5, we now have electrons from chlorine, 5 of them, will now enter into the single orbitals and pair them up. There's 1 here, 1 here, 1, 1, 1. So they are about 1, 2, 3, 4, 5 single orbitals. The 3p's and the 3d's. So 1 electron from chlorine, since there are 5 enters here, there is a dotted line for it. 1 from chlorine, another 1 from chlorine, making it up to 5. So the scheme here will have 1 of the SUs plus 3 of the P's used, PS, PY, PZ, then plus 1 of the D's used. That gives us 3, gives us S, P, 3, and then D. Hybridization scheme in trigonal bipyramidal molecules. So that is it. Write it on top. 1 of the S, use 3 of the P's, and then 1 of the D's. So 1 of the S, 3 of the P's, and 1 of the D. That gives you sp3. D. Hybridization. So the next example we have on the whiteboard is an octahedral molecule. Octahedral because it conforms to the formula ABC that we used initially in this video, whereby the central atom has no lone pair, bonded to 6 atoms. So octahedral molecules have sp3d2 hybridization. So let's write that the electronic configuration of sulfur with 16 atoms, 16 electrons, sorry. 1s2, 2s2, 2p6, 3s2, that is 10, 12, and then 3p4. So having done that, we're going to draw the orbital diagram or box for sulfur. 1s has 2 electrons, one up, one down, in accordance to Pauli's principle. 2s has 2 electrons, one up and 1s and down. Then 2p has 6 electrons, whereby Horn's rule is a p orbital divided into, or p energy levels divided into 3 orbitals. 1, 2, 3, remaining 3, 4, 5, 6. Move to 3s. 3s has 2 in it. Then we'll have 3p. 3p is also into 3ps, 3py. You still share the 3p electrons in the same way as you shared the 2p electrons. So 1, 2, 3, remaining 1, that becomes 4. Now, sulfur, can sulfur hybridize in this way with 6 fluorine atoms? No, because for sulfur to hybridize with 6 fluorine atoms, it must have spaces to contain 6 electrons from fluorine. And as I said before, yes, I wouldn't need to draw these ones because this one corresponds to a noble gas neon. So my interest should be on the last 2. But if you draw it, no problem. So it won't waste time. Just like the one I did in phosphorus, I didn't draw these 2. Interest is the last 2 orbitals. So now, this is ground state. So in excited state, so that sulfur can be able to accommodate the 6 electrons from fluorine. I have 3s here. Okay, excited state, electron from the 2s move, yes. From the 3s move. We want to bring in the 3d orbital. The 3d orbital. So the elements in the third period, like phosphorus and sulfur, might hybridize with, in excited state, with the 3d orbital. So we're going to draw the 3d, not 4s. The energy difference between the 2 orbitals is very small. So we can use 3d. So we have this. So electron, let's just put 1 electron from the 3s. Okay, let's just fill. This is already, let me just fill it up, then I can now do the citation. Fill it up first. The way it is there. Good. So in a certain state, 1 electron from 3s will jump into an empty 3d, meaning 1 here. 1 from 3ps will also move to make it single into an empty 3d. So when I have 1, 2, 3, 4, 5, 6, 6 unpaired, accommodate the 6 fluorine electrons. So in SF6 now, we now have 1 from sulfur and an electron from fluorine, filling it up. They draw the 3p containing sulfur electrons 1, 1, 1. Bring the electron from fluorine to fill it up. They draw the 3d containing 2 of the sulfur electrons. You now bring also 1, 2, 3, 4, 5. You now bring also 2 fluorine electrons to fill it up. So having done that, we can now count. We'll use 1 of the s electrons of orbital, 3 of the p for hybridize, and 2 of the d's. That gives us sp3d2. sp3d2 hybridization pattern. So let's see what we can take hybridization scheme in hydrocarbons. So let's quickly look at the hybridization scheme in methane, a molecule with tetrahedral shape. So methane is CH4, the central atom is carbon, the EC, 1s2, 2s2, 2p2. The ground state EC, the orbital diagram, you see the 2 in 1s, the 2 electrons in 2s, then 2p, according to Horn's rule, shared 1, have an empty 2pz. And then carbon normally has a valency of 4. In this case, you're seeing only 2 unpaired electrons. So what happens to carbon? What are we going to do? So carbon must maintain valency of 4 to bond with 4 hydrogen atoms. So what it means is 1 electron from the 2s will be promoted by when it absorbs light energy we move to 2ps. So this is the excited state. You have 1, 1, 1, 1, 4 unpaired electrons to accommodate the 4 from hydrogen. So in methane, the hydrogen electrons will now fill up 1 in 2s, 1 in 2ps, 1 in 2py, 1 in 2ps, making it 4. We now have S and then 3 of the P, sp3 hybridization formed in alkanes or in methane. So let's look at hybridization in 18, which is somehow different from other hybridization we have studied. So 18 is C2H4, so we have 2 carbon atoms here. In 18, each carbon atom has 3 sp2 hybrid orbitals. You can see the lobes 1, 2, 3. 3 sp2 hybrid orbitals. This one 1, 2, 3. 3 sp2 hybrid orbitals. Now, one of the hybrid orbitals at the extreme will now form a sigma bond or single bond with hydrogen. The hybrid orbitals will also form another single bond with hydrogen atom. At the other extreme, this one forms a single bond with hydrogen atom. This one forms also a single bond with hydrogen atom. You can see it, a sigma bond formed here. So having done that, then the remaining 2 sp2 hybrid orbitals will also overlap with each other to form another sigma bond here. So this is another sigma bond. So we have this form here. Then what then happened? The unhybridized p orbital. The unhybridized p orbital, you can see that this p asterisk means unhybridized. As I said, each carbon atoms has 3 hybrid sp2, 1, 2, 3 for this one, 1, 2, 3 for this one. They all form sigma bonds by overlapping. While the remaining p orbital is unhybridized, they will not overlap. So this one will have an overlap to create what we call a pi orbital. This and this lobe and this other lobe overlap up the plane. This one down and this other one down the plane will also overlap down the plane to give you a pi bond. So that is the hybridization scheme described in 18 molecule. So finally we discuss hybridization scheme in ethyl molecule. Ethyl is an alkyne with the formula C2H2. In ethyl, each carbon atom has 2 sp hybrid orbitals. You can see the 2 by the side, and these 2 sp hybrid orbitals. So the sp hybrid orbital of this carbon we overlap with hydrogen at the extreme to form sp orbital, a sigma bond. The one will also overlap with hydrogen again to form a sigma bond here. Then the remaining sp, the 2 sp from each of the carbon will not overlap head on, overlap to give another sigma bond there. So we have sigma bond, sigma, sigma bond. Now these ones I did not label are now these 2, remaining 2, their lobes are unhybridized. Yes, and are not hybridized. So they overlap by laterally. So this can overlap with this. This will overlap with that. This overlaps with this. This overlaps with that to give you a pi or give you pi bond. So that is the description of hybridization or bonding in a ethyl molecule. So we have come to the end of today's tutorial. Thank you for your time. Thank you for your interest in this lecture. Share our videos to students that need a video, no matter how the school they are, to schools, high institution, first year students, A-level students, people that need this video. There are plenty of them that need the knowledge. So you cannot hold the knowledge on your own. So share the video and then let somebody know today, know something from you today. So share and help somebody out. So thank you for listening and thank you for your time. If you're not subscribed, tap on the subscription button and then get subscribed to the channel for more tutorial. Thank you.